Hi, my name is Carlos Gerardo Lopez Castro, and this is one of the different projects that my team and I are working on at the Nanophotonic and Photothermal Techniques Laboratory of the National Polytechnic Institute in Mexico City. Photothermal techniques consist of the generation and measurement of thermal waves on various substances. By analyzing the properties of these waves, such as amplitude or phase, the thermal properties of the sample can be obtained, specifically the thermal diffusivity and diffusivity. By combining these parameters, we can also obtain the thermal conductivity and specific heat of the samples. The thermal wave resonant cavity technique consists of measuring the complex signal of the piezoelectric sensor as a function of the cavity length, and by means of a locking amplifier to approximate the experimental measurements of phase and amplitude to a linear equation, where by finding the slope, we can finally obtain the value of the thermal diffusivity. By introducing the beam of a laser with a fixed frequency into the metal film of the cavity, an unradiative de-excitation process occurs that generates thermal waves within the sample detected by the piezoelectric sensor. This image shows the resonant cavity we're working with in this project. The experimental setup consists of the components shown in this image. Here we can see that the linear actuator is controlled by the data acquisition card, which is in turn connected to both the computer and the locking amplifier, which ensures we obtain the signal measured with the piezoelectric signal sensor attached to the container. Once a baseline was established for the thermal diffusivity values of pure resin, composite samples were prepared using graphene nanopallets or GNPs. A total of 5 samples were produced with concentration of 0.02, 0.05, 0.06, 0.10, and 0.12 weight percentage. Increments in the thermal diffusivity of the composite were obtained within a range of 16% and 33% compared to the value for pure PMMA resin, which was used in this experiment. Measurement 1 in the graph corresponds to the 0.02 weight percentage concentration, measurement 2 to the 0.05 weight percentage, and so on. One thing we can note in these results is that the higher the concentration of GNPs, the higher the thermal diffusivity. We saw fit to show this in the graph in the next slide. The measurements conducted on the nanocomposites show a semilinear pattern on the increment in thermal diffusivity by the concentration of GNPs. While the number of measurements conducted is only representative of a range of concentrations, more studies with higher percentage of GNPs could show a different pattern of increment or even saturation. The results showed the high sensitivity of the thermal wave resonant cavity technique, which is a powerful tool for measuring the optical and thermal properties of nanofluids. It can also be concluded that the present experimental setup not only provides measurements within the expected values for the thermal diffusivity, but it also provides a better layout for the consisting modules when compared to prior experimental setups that have been used to obtain thermal parameters.